Hello everyone, my name is Krunal Bondre. I am third year student at GHRCE Nagpur. This is my EV201 Capstone project. This EV powertrain contains a motor controller and a BMS. Let's begin with the motor. This is a 3-pole BLDC motor built by me. To build this motor, collect all the required components. The rotor is constructed using bearing and neodymium magnets. For the stator poles, I wound 25 SWG copper wire around an iron bolt exactly 200 times. The motor is connected in star connection. The star connection ensures that the current flows correctly between the phases, enabling smooth communication and stable motor behavior. The difficulty that I faced in making this motor was the air gap between the poles and the rotor. The poles are placed 120 degrees apart from each other. The coils in the BLDC motor are arranged in a circle 120 degrees apart to generate a balanced magnetic field that drives the rotation of the rotor when powered by a controlled DC source. A perfect placement of magnet and coil in this motor enhances magnetic field interaction and generation, so it helps to rotate the rotor continuously. FEMM software will be used to gain a basic understanding. FEMM is an open source software package for 2D finite element analysis of magnetic problems, including both magnetics and AC problems. Here, a graphical presentation is displayed. We can observe the generated torque, total current, and flux linkage in Webers. The next is motor controller that can manipulate position, speed, or torque of the DC motor. Without a motor controller, it is not possible to rotate a DC motor at a variable speed. These three are motor controller modules. Each motor controller module needs a purple PCB board, one P-type MOSFET, one N-type MOSFET, two BC558 transistor, two 10k ohm resistors, two 330 ohm resistors, one 330 ohm 2 watt resistor. By soldering all the components on the PCB, here the MOSFET serve as electronic switches in the motor controller circuit. They are controlled by a microcontroller to turn on and off, allowing current to flow through the coils in the BLDC motor. This controlled flow of current produces necessary magnetic fields that interact with the magnets on the rotor, resulting in rotation and torque. The motor continues to rotate until the signal from the microcontroller changes, turning off the MOSFET and stopping the current flow. Here Q1 and Q6 are activated, which energizes coil U and coil W. In this configuration, coil U is repelling the magnet while coil W is attracting it to produce a push-pull motion. We can change the speed of the motor by adjusting the duty cycle of the PWM signal sent to the MOSFET. The lesser the delay, the maximum the speed, and vice versa. The next one is our battery management system. It has functionalities like keeping the cells balanced in the battery pack, monitoring, protecting, charging and discharging management, diagnosis, communication, and data management. The BMS consists of an microcontroller, temperature sensor, DHT11 sensor, NTC sensor, and 12-volt charging port. The batteries are typically mounted on the backside of the battery management system. In GUI, it shows the system details like how much time the BMS is running, the room temperature, discharging transistor temperature, etc. This is my serial number for BMS board. Here we can see the report for cell 1. It contains the temperature of cell 1, voltage, state of charge of cell 1. Either it is charge, discharge, balance or unbalanced. In our condition, both cells are balanced. For balancing, we used the switch resistor balancing method. Similarly for cell 2. How much current is consumed by the motor in BMS? This is charging button and this is a discharging button. We can plot graphs to visualize and analyze the system. Here we can see the battery pack voltage. In this part, cell 1 temperature and cell 2 temperature. The temperature is collected by the NTC sensor placed in cells, and the ambient temperature is called the room temperature. Here cell 1 and cell 2 voltages are compared. In this graph, cell 1 voltage is compared to the cell 1 temperature. Similarly for cell 2. Current output over time. This is a variation in current with time as the battery discharges. In this particular graph, cell temperature is shown as the current output varies. In this particular graph of transistor temperature compared to time, it is most important to monitor the discharging transistor temperature for the reliable working of the battery. This shows both cells are balanced or not with respect to time. I simulated the thermal simulation on Simscape to monitor the discharge temperature by IC. I observed that with a heatsink, the heat dissipation is greater. This is our I2C communication part, which is the communication medium between two Arduinos. In this, two lines are used. The first is the data line and the second is a clock line. A common ground is connected between them. They are connected in A4 and A5 in the motor controller Arduino. It can deliver a speed of 400 kbps. It uses a 10-bit or 7-bit adjusting system to transfer data between them. The reader, also called as slave, is the Arduino connected to the motor controller circuit, and the writer, also called master, is the Arduino connected to the monitoring system. It is essential for monitoring and controlling the motor's performance. The exchange information helps ensure the proper functioning and safety of the motor. It enables the user to control the motor and receive feedback on its status. For example, if signals indicate that the battery is low, the motor controller may adjust its power output accordingly to prevent damage to the motor or reduce performance. Similarly, if the temperature of the battery is too high, the signal could trigger the controller to slow down the motor speed. This helps maintain optimal operating conditions for the motor, resulting in the better performance of the motor. Now we will see the full functioning of the EV Powertrain Prototype. Thank you.